This is video 6E. It's all about how to predict if a molecule is going to be polar or not. A molecule will be polar only if these two conditions are met. It must have polar bonds. Thinking back to video A, I believe, polar bonds are between 0.5 and 2.1 on our dipole moment or electronegativity difference scale. It has to have polar bonds, and it has to be asymmetrical. It has to be not symmetrical. So which of these could be a symmetrical molecule? If we look back at our shapes, if you have a linear shape, you can look at that and say, well, yeah, thinking about mass, I can cut that down the middle and fold it, and it would look the same. It would be symmetrical. Trigonal planar is also kind of easy to see, to visualize. If I cut it down the middle, it looks to be symmetrical. But what happens when we get into these 3D shapes like tetrahedral? That's harder to visualize. It's harder to see. So we may have to change what our mental definition is for if something is symmetrical in this particular case for these molecules. If it's symmetrical, again, we're thinking primarily about the central atom. If it's symmetrical, this central atom is being pulled in equal directions, and it won't move. It's feeling a tug from each direction equally. So here's 1, 2, 3. That's symmetrical as well. This central atom is being pulled top, bottom, left, and right equally. So if the tug on the central atom is equal, we're going to say that it's symmetrical. So in order to be a polar molecule, it has to be asymmetrical. That tug on the central atom has to be different in certain directions. So here's your how-to list again, step by step. In order to predict if something's polar, you always have to draw the Lewis structure. Drawing the Lewis structure, predicting the shape, we already did that. Identify polar bonds, again, between 0.5 and 2.1. Then you have to determine if it's symmetrical to finally, overall, determine if the molecule is polar or not. If your molecule is polar, both conditions have to occur. It must have polar bonds, the 0.5 to 2.1, and it must be asymmetrical. If it's a non-polar molecule, it can have either or. It's either no polar bonds, so they're all between 0 and 0.5, or the molecule is symmetrical. Let's talk about some examples. Here's the Lewis structure for water. To simplify that, we have our oxygen with 2 hydrogens, and there's 2 lone pairs. So we're going to call that bent 2. Looking at the structure, does it look symmetrical? Do you think these hydrogens can pull on this oxygen as equally as lone pair? No. Whenever you have a lone pair, you're definitely asymmetrical. If you see a lone pair, you're already asymmetrical. So that's part 1. Good. Now I have to check if it's a polar bond. Where do I have to look for that? I have to look at my electronegativity chart. Oxygen on the electronegativity chart is 3.37. Hydrogen is 2.2. Subtracting those, pretty obvious to see. 1.17, does that fall between 0.5 and 2.1? Yes, it does. You have to have both conditions to say that water is, in fact, a polar molecule. Our next example is carbon dioxide. Here's my carbon. Carbon dioxide means I have 2 oxygens. What shape is this? I have 1 cloud here and 1 cloud here. Anything with 2 clouds has to be linear. What's this carbon experiencing? It's being pulled to the left and it's being pulled to the right equally by oxygen. Therefore, this molecule has to be symmetrical. I don't even have to look at the numbers on the electronegativity chart because I know when it's symmetrical, it has to be non-polar. Looking at 2 more examples. BF3 and comparing that to HBF2. So really the only difference here is a fluorine. Here it's a hydrogen. So looking at this molecule, the boron is being pulled in 3 directions, but it's being pulled in 3 directions equally. Therefore, it's symmetrical. Since it's symmetrical, it's not polar. It doesn't have any of those partial positive, partial negative parts to it. HBF2, now it's not symmetrical anymore because hydrogen pulls with a different power. Hydrogen on the electronegativity chart is 2.2. Fluorine is 4.0. Obviously, the fluorine are going to have a stronger pull for those electrons. These guys will have a partial negative end because they have a higher electronegativity. They have a stronger desire for those electrons. When the electrons are pulled down to the bottom, these fluorine parts are going to have the partial negative charge. Up here then, this would be the partial positive. So this is polar. How do I know? It's asymmetrical, and it must also have polar bonds. You can check any of the partial bonds to see if they're polar. As long as you have one polar bond, then you can say your molecule is polar as long as it's not symmetrical. So we said it's not symmetrical. Now we have to subtract some numbers to see if I fit in that 0.5 to 2.1 scale, but I need to know the number for boron. If you look back on your chart, 2.02 for boron. So this hydrogen-boron bond, 2.2 minus 2.02, is not going to be polar. That looks to be nonpolar. However, this bond right here between boron and fluorine and this bond right here, 4.0 minus 2.02 is 1.98. 1.98 does fall in the polar range. So it has this bond that's polar and this bond is polar. As long as you have one and you're asymmetrical, we can say that that molecule is overall a polar molecule. How about these examples? Here's water with its Lewis structure. We said it has a lone pair, so this is asymmetrical. And this guy also has to have a lone pair, so it's also asymmetrical. Water and ammonia are both asymmetrical. But if we look at methane, here's my central atom. Methane is being pulled in 4 directions, top, bottom, left, right, each by hydrogens. Since it's being pulled equally in all directions, this is symmetrical. So I know automatically that this is non-polar since it's symmetrical. These two, now we have to look at some numbers. If you look at water, oxygen is 3.37. These would be my hydrogens at 2.2. 3.37 minus 2.2, 1.17. This has polar bonds, and it's asymmetrical, so this must be a polar molecule. Looking at ammonia, here are all my H's, NH3. Again, we said hydrogen was 2.2. Nitrogen, if you go and look back on the electronegativity chart, nitrogen is 2.81. 2.81 minus 2.2 is 0.61. So this also has polar bonds, and it's asymmetrical. Therefore, ammonia is a polar molecule. We got to look for two things. We have to look for asymmetrical shape, and you have to look for some polar bonds, at least one polar bond. Then you can say it's a polar molecule. Two more examples. We already looked at carbon dioxide. We can look at its numbers, but we don't have to because carbon is being pulled in two directions, right and left, equally by two oxygens, so we know it's symmetrical. When something is symmetrical, it's nonpolar. That's the case for linear molecules. But in this example, carbon's in the middle. Here I have a hydrogen. Here I have a nitrogen. Hydrogen's number is 2.2. Nitrogen's electronegativity value is 2.81. So nitrogen has a stronger pull for the electrons than the hydrogen does. Since the numbers are not equal, it's asymmetrical, so that's good. Oops, C-A-L. Asymmetrical, that's part one. Now, do I have polar bonds? What's the one piece that I'm missing? I need the value for carbon. Carbon is 2.56. Do I have any polar bonds? 2.56 minus 2.2. That's not polar. That's a nonpolar bond. How about 2.81 minus 2.56? This one's harder. 7, 11 minus 6 is 5. 7 minus 0.25. That's also nonpolar. So even though my shape looked asymmetrical, I did not find any polar bonds here. Therefore, this shape is also nonpolar.